Thank you, Ben. Actually, I would like to thank you for the invitation and for all of you taking some time off to have this conversation. So I would like to put it more like a conversation. So whenever you have any question, just feel free to stop me. And I still try to make it on time. Okay. So. Uh, okay. 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 I got my PhD in the US from University of Notre Dame, and currently I'm a professor at HKUST with both the Chemical and Biomolecular Engineering Department and Division of Environment. My interest is actually developing functional materials, okay, smart material and multifunctional materials that have applications in health and environment, okay. And why is it, I think that this area is actually a very interesting research area. This is because as of 2 weeks ago, we have about 7 billion reasons to think about health and environment, okay? As the population grows, this becomes a much more critical issue in the coming years, okay? And particularly in Hong Kong, okay, we are not actually stranger for a lot of this problem that have been occurring. When I came back in 1996, okay, 97, I experienced the H5N1, okay, when they start to kind of kill off all the chicken, okay, it's the year wherein you don't have chicken for Lunar New Year, okay, and then after that we had the experience in SARS in 2003, and more recently it's about 2009. So we can say almost like every 5 years since I came back to Hong Kong, we had this episode of a major outbreak. And each time that this happened, it's not only had a huge economic impact, but also it's had a big changes in people's lifestyles and habit. You know, like beforehand in Hong Kong, like everybody who are decent enough will want to have live poultry. Okay, so you need to have live chicken. You know, but now after the H5N1, nowadays you cannot have that. Okay. Before 2003, it's very rare that you would see Hong Kong people wearing masks, okay, when they get sick, okay. So this is a very huge, like, life-changing event, okay. There's also the word they started to have this like individual packaging for food and baked goods, you know, from the bakeries. Prior to that, you don't have it, okay. So these are major, very traumatic events that also have very big life-changing for us. Now, why do I find that this area is a very interesting field for me to look into? Because one thing is, like, each year there's about 1 billion people who get sick of just influenza. I think each one would be sick for at least once, okay, because of either flu or a cold virus, okay? And each time you have a major mutation or change in the virus strain, then it becomes more serious. More people get sick and more people die, okay? So that's become a very important issue. And then a lot of the viruses, especially here in China and Asia, most of them also afflict, okay, typically the elder and the very young. Like, for example, the hand, foot, and mouth disease. And in a hospital, because of the prevalent use of antibiotics, and actually, as we mentioned, like wrong usage of antibiotics, there's the emergence of the so-called drug-resistant microorganisms, or MDRO. And these are very serious, okay, because, like, for example, the superbug, which is the NDM11, actually can resist major antibiotics that is currently being used for treating this bacteria. So it becomes major issues. And then in Hong Kong, of course, we have the major problem about spores, okay? Either they are bacteria or fungal or mold spores, okay? Spores are typically very difficult to inactivate, okay? Because they have very strong coatings. And some of the spores that probably most of you have heard about are anthrax spores, okay? These are bacterial spores, same family as the Bacillus subtilis, okay? And like back in 2001, when they have the scare in the Capitol Hill in the US, they have to actually close it and fumigate it for 3 days in order to make sure that they're eliminated. Therefore, stopping disease transmission is therefore very critical for individual and community health. Okay, and one of the very important issues that it's better to go for preventive measure than cure. Preventive measure tend to be much more inexpensive, much more accessible than cure itself. Okay, so that is where we are coming from. Okay. Disease transmission, basically the way that disease transmit is basically depends on many issues. Number one, the microbes or microorganisms that we are talking about, how virulent they are, how fast it can infect people, how people are susceptible, okay, and the different pathway and route that are available, okay, for the transmission of these pathogens or disease, okay. And one way typically people are get used to is the direct way, okay. That is one possible way. Somebody sneeze, somebody cough, okay. You aerosolize, okay, a lot of these microorganisms, and they will stay in the air because when the droplet leave your mouth, it dehydrates very quickly and they become very small and they can persist in the air for a long period of time. And even if they settle down, sometimes they get re-aerosolized when they are stirred back up, okay? And most of the microorganisms could stay for a long time. Actually, I'm coming from an engineering background, so a lot of things that we do, okay, in comparison to science, like science, usually a lot of the things that the scientists will do are driven by curiosity. Engineer, it's also driven by curiosity, but at the same time, we have a very strong motivation to actually improve people's life, okay? We are looking more on application. So whatever you do in terms of technology, if you are not able to translate it into a commercial product, it's not going to have a very big impact on any people's life, okay? It had to be somehow made available as broadly as possible. So there's a major driving force for a lot of my project that we had to consider commercialization at the very beginning, okay, when we embarked into these things. So we had to look at a lot of practical issues. And some of the practical issue had to do with people, okay? Because people behavior sometimes can interfere on how effective a system can work, okay? And this is something that we have done. So the first thing that we had done is like to work on improving the air purification system, air purifier in particular. This particular grant had actually been allocated to us during the SARS period. Initially, our main purpose is to improve on air pollution, not looking at pathogen. But 1 month after we got the funding, the SARS happened, and then we were forced to work with pathogens. So we quickly realigned the group, okay? And then we look at pathogens, and then we develop methods that can be very effective in terms of eliminating different type of pathogens from bacteria to fungal spores, and also to that of the viruses. In this case, we use bacteriophage, which are viruses that attack bacteria as a surrogate, because we cannot just release viruses into the environment. And we did field tests, okay, under like the auspices of the Department of Health in some of their clinic during the height of the SARS period. So this is 6-month period wherein we have basically went into clinic during the height of the SARS period to do field testing. And then during that period, basically we had to rely a bit on both like quantitative method as well as survey of the medical personnel and the patient that are done, because we need to look at the actual performance of the system. Later on, this study had been extended to China, okay? So this was done in a Chinese hospital by a Chinese colleague, okay? Wherein they actually did more detailed study in the hospital settings. So all of this come with the conclusion that the system is quite effective in terms of eliminating both airborne bacteria and viruses, okay, that are present in real environments. Now, the other way that disease can be transmitted is actually indirect, and this is actually typically, I would say, the most typical way that people pick up diseases, because like a lot of the microorganisms can survive in the environment for a relatively long period of time, okay? And then and people may just pick them up, okay? And then when you touch your mucous membrane, like your eyes, nose, and mouth, okay, you can actually inoculate yourself with this virus or microorganisms. And then what happens if you're susceptible, then you would get sick. And then just to see a typical way that transmission happen, you know, people, of course, sometimes you sneeze, you're polite, so you cover it with a tissue and you sneeze. Okay, fine, that's great. You reduce the airborne. But then what happened is like your hands get dirty, okay? The tissue get dirty. And then what happened is that you start to touch different materials, and then you spread it, okay? And then throughout the day, you can actually monitor it, okay, during like simple things that you're doing. And throughout the process, you're actually contaminating your environment. And the next person can pick it up readily. And then, in fact, this is very true because a survey that have been done by other groups, not our groups, they actually found in most surfaces in public area contains like an enzyme marker that comes from saliva. Okay, about a third of surface have that. And then if you find that, you would typically find blood and stool, okay, markers, okay? So environment-wise, typically public environment can be quite dirty, okay? So, and then also, under these circumstances, a lot of the viruses and bacteria can actually stay there, okay, for more than 24 hours to more than a week and remain infective. Okay, and that actually an experience that had been proven during the SARS period. In fact, like that is why there was a huge campaign by the local government, and which is later adopted in other countries, in order to promote cleaning. Okay, hand hygiene and cleaning as a way of like basically intervening and stopping the transmission of these diseases. However, a lot of time cleaning may not be sufficient because like most of the disinfectant and cleanser clean and disinfect at that moment. And once they dry off or they evaporate, you don't have any more of this disinfecting property. So that means to say the next person who touch it can contaminate it, and then the following person who touch it will pick it up. Okay? So, so we went to develop this smart antimicrobial coating. Actually, the way that we went into this is relatively indirect. That was toward the early year of 2004. One of the company that we are working with, they have a good relationship with Beijing government. And at that time, they did know that the Beijing is going to host the 2008 Olympics. And at that time, the Beijing government is very concerned that SARS is going to be a recurring event. Okay, so they said, okay, if that happened, what should we do? So they have a panel of experts, including like physicians and other peoples, wherein they come up with a list of criteria, okay, of a technology, okay, that had to be developed in order to be able to make it safe. And then basically this company shared with us some of the criteria. Okay, the criteria, of course, number one, it have to be simple and easy to use and inexpensive, because the idea that they have is to have a coating material to coat most of the stadium, okay, or benches, okay. Secondly, it had to be very fast and effective. Their benchmark is 90% reduction of antimicrobial that come into contact with the surface within 30 minutes. Now, you would say, well, there's a lot of bactericidal surface or antimicrobial coating that are currently commercially available. Why don't they just go out and buy them? Well, commercially, a material can be said to be bactericidal or antimicrobial if they can reduce the bacteria by 90% after 24 hours. After 24 hours, okay? Now, the problem is that during the 24 hour, if you don't reduce it sufficient enough, other people can pick it up. And 90% is not really make many sense, because if the bacteria, you're talking about millions, you reduce it by 90%, you still have 100,000. If you have billions, you still have 10 millions bacteria on the surface. So you need to have much more effective means of reduction. You have to be long-lasting. The requirement is 30 days in one application, because Olympic lasts for about 28 days. So that is why they have to come up with this 30 days. They want it to be smart so that it can do self-disinfection, so they know that if it gets contaminated, it will self-disinfect and self-clean. Okay. Furthermore, okay, it had to be safe and environmentally friendly. And there are other attributes that they wanted, because they wanted this to be very discreet. They wanted to be, okay, odorless, colorless, tactileless. Okay. But once we come up with that formulation, the first question that they asked me, how would we know that it had been coated? Okay. So you know people, how they think, okay? So the way that we approach it is like we borrow things, okay? A lot of time being creative doesn't mean that you have to create something totally new. Being creative means that you know, you are aware of what technology is available there. You know how to borrow it, but at the same time how to assemble it, okay, in a way that will be acceptable. Now, if I develop something totally new from scratch, I will be in trouble. They won't be able to use it because I don't have the supply chain to manufacture it. Okay? So if it is something that needed urgently, you need to use material. Number one, have proven history of safety, have proven history of use. It had to have a supply chain. It had to have manufacturing infrastructure available. Otherwise, you won't be able to implement it, however elegant that solution is. Okay? And that is why it will need to take 10 to 20 years if it is a totally new material, because you have to build up all those infrastructure to bring your product into the field. So we had to consider all of this when we had to do that with a lot of constraint. The product had to have a proven history, had to be approved by US EPA and US FDA, and then it had to be cheap. So we had to develop a manufacturing process. So in this case, we borrow something from drug delivery. So we use like the smart polymer system. We borrow something from cosmetic, okay, wherein we use water and oil in water emulsion, the one that you use for cream, okay, to make it into very friendly, environmentally friendly system so that you can use it in water-based, okay. So at the same time, we have to do a lot of skill set that we have to go in order to design and manufacture the material. Most people will say, well, how do you do that? If it is some old material, how could you make something new out of it? The first thing that I will tell you, well, a piece of iron is still a piece of iron whether you use it in a bicycle or in a space shuttle. It's just like how you design and engineer it. That is the most important issue, okay? So that is what we had done. So the sprayed-on formulation, okay, you can coat the surface, you cannot see it, okay? So that is one of the complaints that they have after they do it. But you can look at it under microscope. Later on, we develop a litmus paper test so that they can just use a litmus paper in order to test whether it's on the surface or not. The formulation itself is already a disinfectant. It's very effective. Okay, it's actually much more better than bleach or alcohol because it can treat most of the microorganisms. We can reach a log 4 reduction in 1 minute. Once it coats on surface, because now it needs some time to release the active ingredient, it takes about 1 minute. It can eliminate bacteria by 99.9%, virus 99%, and spore 99%. So what is the difference compared to the other type of disinfectant? One issue is that other type of disinfectant, when they were dry, they don't have any effect. This one, even if they are dry, left for 30 days, you put it onto a surface that have a culture bacteria, it will have a clear zone because the bacteria are killed around it. Okay, so that is why you have a clear zone. It can last like more than 60 days. Okay, basically these are actual measurement in the lab. Okay, and then if we do a extrapolation based on the amount of the active ingredient that is being released, it actually can last for more than 6 months because 1 month we only reduce around 20%. It also, the material that we put in, we encapsulate is a gas. It's not a liquid. Why do we want to use a gas? Because a gas, even if the surface got dirty, it's easy for the gas to penetrate through all those dirt and kill the microorganism compared to a liquid. So to prove that, what we have done, we did a culture of bacteria, and then we have a coating of this material, and then we put it at a certain distance from the surface, okay? And then what happened, it will clear the zone, okay? So then you can see the paper underneath it saying the type of bacteria that is on the surface. So we say, well, that is a force field, so we can go up to 3 millimeter, okay? It's smart in a sense, like when you touch the surface, the area that you touch, the dosing will increase by 10 times. So it will quickly eliminate any bacteria that would come from touch. Similarly for droplets, okay, so they work very well. They can reach like log 5 reduction in 1 minute. It's also self-cleaning because it prevents any bacteria from clinging to the surface. So it had a detergent action. Like for example, if you don't have any coating on the surface, bacteria can easily form a biofilm and then propagate toward the surface, so making it slimy and dirty. But on the other one, basically it will basically prevent that from happening. Okay, so we have 1 minute. Okay, we did quite a number of field tests. Okay, we do biocidal tests in China because they do have virus lab. We tested for H1N1, Tamiflu resistant H1N1. Both of them are swine flu strain. H3N2, EP71, different type of viruses. Okay, and then it shows that we can actually reduce them 99% in 1 minute. We did many different field tests in different public hospitals in Hong Kong, including Twin Mun Hospital, also like Princess Margaret Hospital for a lot of the multi-drug resistant organism, as well as the, we did clinical field testing in Queen Elizabeth Hospital in their ICU unit. This is done mainly by the doctors, and then we show that we can actually reduce the environmental loading of the microorganism, and also samples that are not encoded have MDRO. Indeed, we had a press conference last year, okay, September 9, 2010, about this technology. Currently, the same, like we always, as an engineer, you have more than one solution for one problem, okay? Or typically, recently we have been working on a material. This one, I can talk about it because we just been granted a patent 2 weeks ago from the US, okay? This is on the nanobottles. The nanobottles idea that we had done is like, we can actually create a texture on the surface and then create like a reservoir on the surface. And then what happened is that during the nanotexturing, we can actually render the surface to be self-cleaning, okay? And then simultaneously, by creating in the nanobottles, we can actually put in antibiotic enzyme into the material like GOD or HRT materials, which can render the surface antimicrobial for long-term applications. Okay, thank you.